Hello all, this is Srikant Boligarla. Here is my final project, classifying heart sounds. First of all, thanks to Professor Zoran, TAs, and also the classmates who helped me on Piazza. Here's the agenda. First of all, we look at the project objective and see how the data looks and see what are the various steps taken to analyze this data before sending it to the model building. Then we'll see how the model looks and the results and some of the challenges I faced and how I overcame them. And then conclusion, demo, and next steps. So cardiovascular diseases are the number one cause of deaths in the world right now as per World Health Organization. So any method that can identify the symptoms early on can have a tremendous impact on global health. In this project, I categorize heartbeats into normal, murmur, and extrasystole. These are different types of heartbeats. They are recorded using a digital stethoscope. The dataset itself is taken from this link from the Heartbeat Challenge. There are dataset A and B in this link. I chose dataset B because it has more number of audio files. And in B, I have also removed the noisy heartbeat sound before I started my processing. I use Librosa, just like in our week 11 class, to process WAV files and then visualize the sound waves, spectrograms, MFCCs. And spectrograms are log transform, short-term Fourier transform of the timescale audio file. And this generates the spectrograms in frequency domain instead of time domain. And then once we apply a inverse Fourier transform on these spectrograms, it generates a MEL frequency or melody frequency cepstral coefficients. These MFCCs are generated into a file as NumPy arrays, and those are used as input to our model. I also resample the audio files using a lower frequency to reduce dimensionality and plotted the violin plots for frequency of heartbeats. And then I also split the data into train, validation, and test. So we train the model on the train data set. We check how good it is based on the validation set, and finally evaluate on the built model on unseen data set, the test data set. This is how the distribution of various sound files that we have. We have about 200 samples of normal heartbeats, 46 extrasystole, also called extrastole heartbeats, and then 66 murmur heartbeats. Let's hear a normal heartbeat sound. It has a lub and dub sound sequence. They are also called S1 and S2. Let's hear one. The wave plot looks like this: S1, S2, S1, S2, S1, S2 for a normal heartbeat. That's the pattern. For an extrasystole heartbeat, you have an S1, S2, S1, S2, sometimes S1 followed by an S1, or sometimes S2 followed by an S2. This could be a cause of concern and should be called out. In a murmur heartbeat, between the S1 and S2, you'll have a whooshing or a disturbance kind of a sound which the doctors can hear better. So here I plotted the MFCCs and their first and second derivatives. For our model building process, we use the generated NumPy arrays in files, the MFCCs, as input with these three output categories. We label them, so this is a supervised learning problem, classification of course, and then the activation function used is ReLU for different layers, but for the output layer it's softmax because it's a classification problem with more than two categories. I also have the Con2D layers, dense layers, flattening and dropouts for regularization, and max pooling to reduce the dimensionality. On data that is not seen by the model, I see an accuracy of 80%. The challenges I faced. So the model building is taking a lot of time, and then refitting that same model without any change in the parameters is a total waste of time. So I saved the model as a JSON and then loaded the model. I used a flag to switch on and off whenever I didn't have to refit or change any parameters at all. The same goes with history. I saved it as a JSON and then reloaded it. And the audio files are taking a lot of memory, so I saved them on my Google Drive and connected Colab to that. And one interesting fact about MFCC is that it decorrelates the features, so that avoids multicollinearity. However, our deep learning models take care of that, so that is not really necessary for us. And the audio files have different size and recordings, so we had to normalize and pad if there are lower in size dimension. So in conclusion, I built a decent model, I believe, using deep learning to classify into these three categories. As next steps, I would like to see if I can apply LSTM by creating a time series kind of input for this data set, and then or try with the bigger data set or different audio file format, and see if I can automate this whole process using Azure ML or Luigi pipelines. Let's see a quick demo, or rather see the notebook on Colab. So this is a quick background of what it is. As I said, there's lub-dub sounds for normal heart category. There's a whooshing sound for murmur between lub and dub, and extra systole. As you see, there's a lub instead of a lub-dub. So instead of S1, S2, it's S1 and S1 here. So that should be called out. So we load the data set, connect to the drive. If you are doing it from your local machine, you can just comment out these first 3 lines. That's clearly mentioned in the documentation I attached with this project. So I again loaded some files here, some wave plots of normal, murmur, and extra systole heartbeats here, MFCCs, linear and log frequency spectrograms. Then I have the first and second derivative of the MFCCs. Then fast Fourier transform on different frequencies are created here. Here is the distribution of the data that we already looked at in the presentation. Again, the same FFT. So violin plot for the frequency. Yeah, MFCCs again. So as I said, MFCCs or MEL frequency septal coefficients are inverse Fourier transform of log transform Fourier transforms. So it is it's kind of a spectrogram of a spectrogram. So that's why it's called sepstral coefficients by the researchers, to differentiate. And then here I'm splitting the data into train, test, and validation. And here are some helper functions for storing the model and loading the model. So this is my base model with the Con2D flat and dense, and this didn't give a very good accuracy. So I built an improved model with some max pooling, some dropouts at 5 and 4%, and then same ReLU and softmax. different runs gave me different accuracy. Here I got 73%, sometimes I got more. But on the unseen data, I got a very good accuracy on prediction. See, about 80% here. And the files that we need to put here are the preprocess.py. I slightly modified it from what it was in the class. I shared this also. And the data can be put in your computer and then placed where the notebook is, or you can connect the drive to this one. And these NPY files are MFCCs generated into a file for normal, murmur, and exosystole. So that's pretty much it. As next steps, as I said, we can try different other models, and if I can find a larger data set, I would like to apply this over there. And there are other format files on the web page. Here, this is where I took the data from. So in addition to WAV, there's a AIF format, and then there's a different data set with smaller number of files, which we can try. And then we can also automate the whole process using Azure ML or something on AWS. And Luigi pipeline created by Spotify is also good pipelining strategy, especially based on files. Once we place a file, it will detect and then start running the pipeline. So thank you so much. That's my presentation on my final project. I submitted all the documentation, code, and the files. Please reach me out on inbox or Piazza. Thank you so much. I'll post the YouTube videos later.